Hello, class. I wanted to do an example first, finding our axial force diagram for a pretty simple example. And then I wanted to figure out, using that axial force diagram, what is the maximum average normal stress? All right, so let's first start by figuring out what our method is. And then once we have our method, we can use it to solve. That's the best way to solve these problems, make sure that we use our time efficiently. So our first step is to draw that diagram. So to find the axial force in this, we're going to need to make cuts. And the interesting cuts are going to be between our forces. So we need to make a cut here between A and B. And we need to make a cut here between B and C. And we need one more cut between C and D. And we can decide which side of the cut we want to work on. For the first one, I'm going to look at the left side because it's a very, very simple cut. If I draw that cut, let's do a free body diagram of A to our cut. We could call this cut AA. We do that cut AA. That's going to look like, okay, well, here's our section. Here's A. Here's our cut. And we're going to have our applied force of 12 kilonewtons here. So there's our 12 kilonewtons. And then over here, we're going to have our internal force. Our normal force is pretty easy to find with that. Our normal force in this case is 12 kilonewtons. That's the first free body diagram. We'll do the second free body diagram after B. And I can look at the left or the right-hand side. I think it's going to be about the same amount of work. So I'm going to call this cut between B and C to be cut BB. And I'm going to say of cut BB. I'm going to draw that cut up here. I've got A. I've got my nut there at B, and then I have the section where I'm cutting it in the middle. And then I'm going to draw my forces in here. This is 12 kilonewtons. Now be careful here. It's very easy to forget that this is 9 kilonewtons up here. It's also 9 kilonewtons down here. So together, looking at this, if I've got 12, 9, and 9, that's going to be 30 kilonewtons pulling this way. In opposition, this normal force has to be 30 kilonewtons by looking at the sum of forces in the x is 0. And then we'll do the last part, take a cut there at CD. Now I could do either side, but the smart way to do it is to take the right-hand side. If I do that right-hand side of that cut, if this is D, I'm saying, hey, this is a free body diagram of cut CC. I'm going to call this C and C. On this side, I've got 22 kilonewtons. On the other side, I know my internal force has got to be 20 kilonewtons acting this way. And then I can say, okay, then from sum of forces in the x is 0, I now know that normal force here is 22 kilonewtons. Now let's think about signs in each of these cases. Now in each of these cases, I've got a normal force that's pulling away from my section. That's in tension. This is in tension. This is in tension. Now this is going to the left, but because I'm pulling this way, it's also in tension. So now I've done all my free body diagrams. So the first step is really making cuts. This is cuts. Step 2 is build your diagram. We'll talk about that in just a second. And the third step is finding our max average normal stress, sigma max, as we often call it. And in this particular case, to do that, we need to find area for our cross section. And now the area for this is actually pretty easy. We know it's a rectangular cross section from the sample text. Also, we can calculate it pretty easily because here we're given 35 millimeters. In the text, it tells us that this is 10 millimeters. So I know the height is 35 millimeters. Now you'll notice when I drew this, I used arrows like this. If I'm drawing a small cross section, I can use arrows like this, and it says between these two arrows is 10 millimeters. That's just a very simple way to show that pretty quick and easily. All right, so now once I find my area, I know that sigma max is going to be that maximum stress, right? And they call this P in the calculation, but you can think of it as normal force N divided by our area. And that's a rectangle, so that's pretty easy to calculate. Let's build our diagram. Now that we have our internal stresses and our free body diagrams figured out, let's do our diagram. So our free body diagram is going to look like this. And I'm going to go ahead and label some important points on this diagram. Let's build those out. I know over on this end I have A, I have B, I have C, and I have D. And I start out at A. I found out that my normal force at AA, between those two, between A and B, I'm going to have 12 kilonewtons. There's 12 kilonewtons. And then at B, I have an instantaneous change in force right after the cut there. I have an instantaneous change in force of 18, which brings it up to 30. And then at C, I'm having an instantaneous change of force again. We're going to drop down to 22. So somewhere in between those two, we'll say, hey, that's going to be 22 kilonewtons. So there's my diagram. That's all I got to do. Some students like to shade it. You're welcome to do that if that helps you visualize it a little better. Make sure you have nice vertical lines here. It might be a good idea to use a straight edge. I need to get a large straight edge for me. That's 22 kilonewtons. There's our diagram, something like that. So that's part A. Part B is figuring out what that stress is. To find that stress, we need the area. So sigma max looks like our maximum stress, that's 30 kilonewtons, divided by our area. Now let's be careful about area here. Our area is in millimeters, or sorry, our dimensions are in millimeters. I could calculate this in terms of millimeters. This would be kilonewtons per millimeter squared. That's not the units that we use. We usually use pascals or megapascals. So what I'm going to do is I'm going to convert these over to meters. So this would be 10 divided by 100, or 1,000, 0.010 meters. And this would be 0.035 meters. You could also think about these if you're used to working as a machinist with inches, thousandths of an inch. You could think of this as thousandths of a millimeter of a meter. That's going to help you out. It's definitely 3 decimal places. It's 10 thou, 35 thou. That's a clever way to think about it. When I calculate it, I'm going to put it over here. And this is going to be 0.035. And this is going to give me a pretty large number here because I'm dividing 30 by 2 very small numbers here. So I've got 30 divided by 0.01 times 0.035. When I do that calculation, I get a very large number here. This would be 85,700 kilopascals. How did I get kilopascals? Well, I have kilonewtons divided by meters squared. A newton per meter squared is a pascal. So kilonewtons divided by meter squared would be a kilopascal, which means when I calculate this, I want to leave my final answer in 85.7 megapascals. Right? I want to use megapascals and get us down to 3 significant digits only. All right, so how did we do this? First, we took a lot of cuts to get our free body diagram. Some of these we could probably get away with doing mentally, right? This one and this one are pretty simple. We could probably get away with doing those mentally in the future. This one in the middle, because there's more going on, you definitely want to make that cut. That's going to tell us what our normal force is at each of these cuts. Then we're going to draw our diagram of axial force. Now I forgot something very useful here. I want to make sure I always put that this is our normal force, give those units. And we're going to say this is going to be in kilonewtons. That's all Always when you draw your diagrams, you want to do that. You also want to indicate any important points like I did. A, B, C, and D are where interesting things happen. So we want to label those in our diagram. Once we have our diagram, it's easy for us to find sigma max because we already know our maximum force. So maximum stress is just going to be that force divided by the area of our cross section.